Greetings, friends of chemistry.
What up?
We're doing Module 14 review questions.
Alright. Let's get real here, people.
14 review questions. Let's hear the first one, please.
If two molecules want to react together to form new chemicals, what is the first thing that must happen?
What is the first thing that must happen? They're not going to have a reaction if they're in two separate containers.
So they must be in contact.
They have to be in contact with each other, right? So if you want to have a reaction, you have to cause your chemicals to react to each other, which is not going to happen if they're not in the same location.
Yeah.
All right. I believe that's the answer. Do you have any questions about it?
No.
Seems pretty straightforward. So Martin is writing that answer down. Maybe I should write it here on the chalkboard too. The molecules need to contact each other. Okay.
A chemist runs a reaction at a low temperature and then runs the same reaction again at a high temperature. Which reaction runs faster?
Okay, so we have to think of our principles of reaction, right? We know that generally speaking, the rate of a reaction increases with increasing temperature. So what does that tell us?
It's the second one.
The one at high temperature.
3. Explain in your own words why the rate of a chemical reaction increases with increasing reactant concentration.
Okay, so it has to do with number 1, doesn't it? Number 1 tells us that the molecules, so what happens in a chemical reaction is there's some kind of exchange of electrons, right?
Yes.
So in order for that to occur, the molecules have to contact each other, okay? So if I have, say, a container of gas, and I have the gases at a very low concentration, is it likely that they're going to, if I have one at low concentration, one at high concentration, where are they more likely to interact with each other?
The one at high concentration.
Right, because there's more opportunities for them to get together. Like, let's say you're at a party, and you're the only person in the room.
That's a high concentration.
You're not going to have a very good conversation with somebody.
That's a very high
But if you're a party and there's 50 people in the room, and you can interact, you'll have a lot more interactions. So, so how would you put it in your own words?
It's a party.
Uh-huh. I'm say molecules must interact for reaction to occur. The more molecules at the party, the greater chance of interaction. Okay?
Yep.
So, let's look at number 4 review question, and then I think we'll pause and do a second video.
Mm-hmm.
Okay. You ready to read it?
The chemistry book lists the rate constants for 2 different reactions. The first rate constant is 0.121 over seconds, and the second is 34.5 1 over meter molarity per second. Even though the rate,
Molarity times second.
that's
right?
what I meant to
Yeah.
say.
Uh-huh.
Even though the rate equations for these reactions are not given, an astute student says that the overall order of these two chemical reactions must be different from each other.
Absolutely.
In addition, the student says that the second reaction is faster than the first if the concentration of the reactants are roughly the same. Why can the student make these statements?
Okay. So as you know, the rate constant will have variable units. So when what is the equation for rate? It's R equals K times the concentration of A to some exponent X times the concentration of B to some exponent Y, where we have an equation something like that, okay? So if we've got these two substances, A and B, we would say that the rate of this reaction is going to occur at some constant times the concentration of A to the exponent times concentration of B to the exponent. So how do we figure out the exponent? We figure out, and the rate of reaction, we have to do it experimentally. We're not really doing that a lot in this course. We're mostly looking at experimental data that other scientists have gathered. But
yes.
So let's imagine that this X is of 2. That means I'm going to say molarity squared, right? So when the rate is always in terms of what, Martin?
In terms of K times A times B.
The rate is molarity per second, right?
Okay.
So we're going to have molarity per second. It's going to equal some constant times, molarity squared, maybe times molarity, right? So we're going to have different numbers, different powers of molarity depending on this exponent, which has to do with the order of the concentration, right?
Yes.
So let's look at the first statement. The overall order must be different from each other. In the first reaction, the K units are 1 per second.
Yeah.
Okay? That tells us that none of these molarity units are what? Are squared. One of them isn't even there. Otherwise, we'd have molarity in our units, right? So one of them is to the 0 power, right, which will give me no molarity, and the other is just to the 1 power. How about the second one? The second one has, because this is in terms of molarity, so they're going to cancel each other out.
Yeah.
So however many molarities I have over on this side, right, there's one left over. There's one more than this side, which means that it's something molarity times molarity or molarity squared, which is giving me a molarity here. So that tells me that this is a higher order.
Yeah.
Right, because of these K units. Okay.
Mm-hmm.
So that's the first statement. In addition, the student says that the second reaction is faster than the first if the concentrations of the reactants are roughly the same. Why can the student say that?
Well, if the rate constant is greater, the rate will probably be greater as well.
That's right, because the constant is part of the equation. So if the concentrations are approximately the same, then the one with the higher constant will have a higher rate. Otherwise, the other things being equal. Okay, so does this make sense?
Mm-hmm.
Good. We're going to pause the video here, and we'll come back with another video for review question 14, number 5.